welcome to choose maths and physics classes for today. In our physics class, we are considering the topic elasticity. Elasticity 2. I believe you must have followed the first teaching on elasticity. Elasticity 1, wherein we discuss the concept of elasticity, the meaning of elasticity, which is a tendency of a material to regain its original form after undergoing a stress. And then we consider the Hooke's law. Hooke's law, the original of first or empirical law that governs the phenomenon of elasticity. And Hooke's law mathematically states that F is directly proportional to E, or F for compression, and which implies that F is equal to KE, or F equal to minus KE, depending on if a material is being stretched or compressed. This is Hooke's law, which is the empirical equation of elasticity. Hooke's law. Then, before we delve into calculation, which today's class will focus on, let us discuss briefly about work. Work done or energy used in stretching or compressing a material. Work is usually done when a material is being stretched. Stretching or compressing a material such as a spring requires utilization of energy. So work is usually done. And when a body is stretched or compressed, it now possesses energy due to its new state, which is potential energy, otherwise known as elastic potential energy. Elastic potential energy. So, work done or energy used in stretching or compressing a material can be calculated as follows. Of course, you know, when a body like a rubber is stretched with a catapult or spring and is released, it does work. If you stretch your catapult and release it, assuming you attach an object like a stone to it, the stone release will do work elsewhere, which means it has possessed elastic potential energy by stretching the material. So, the work done in stretching it or energy it possesses depends on the force of drag of the rubber and the extension produced. Of course, we know that work is force times distance. And then the average force multiplied by the distance. See, we use the term average force because the force increases from zero. So we use the term average force. And this gives us Fe over 2. This is the work done. This gives us a measure of the work done in stretching or compressing a material. Of course, from Hooke's law, we know that F is equal to K, and substituting for F equal to K in this relation, we now have work or energy equal to Fe squared over 2. This is another relation for calculating the work done by an elastic material. Take note of it. We are now qualified to do some calculations. We are now qualified to do some calculations. And we start this way. Join me in this. Look at this. An elastic wire of original length 2.0 meter extends by 3.0 cm. Extends by 3.0 cm when a force of 4 Newton is applied. Determine the extension. We gather the quantities given from the information here. We have that the original length is 2.0 meter and the extension is 3.0 cm, which you convert it to original or the SI unit, which is 3.0 cm divided by 100, that gives you 0.03 meter. That's the extension produced, whereas the force is 4 Newton originally. Something is missing here. We write our formula of Hooke's law, and that is F equal to KE. Remember that? You substitute F is 4. Under F here, you write 4 Newton equal to K unknown multiplied by E. Extension is 0.03 meter. You make K the subject of the relation. K equals 4 Newton over 0.03 meter. And checking that out with your calculator, that gives you 1,200. Wait there. Check it out with your computation machine. Check it out with your computation machine. It gives you what? 1. Newton per meter. And that, can I have the exact value from the machine there? 133 what? That's one. Now, to find the extension when force increases to F equal to 12 Newton. Using the same law, Hooke's law, F equal to K. F is 12 Newton. K has been found 133.3 Newton per meter multiplied by E, which is the required variable and making it the subject of the relation E equals 12 Newton divided by 133.3 Newton. So there you are, watching me. Divide 112 by 133.3. Your result should be in meter. That is it. Take a look at this before we forge ahead. B. We've answered question A. Question B says, work done. Work done or elastic potential energy stored in the material is equal to Fe over 2. And use any of those relations. We go with this one, Fe divided by 2. The F is 12 Newton times the extension produced is what we have here. Punch it and tell me, as you are watching me now, what you have from this degree. That gives me 0.0. We punching gives you what? 0.09. That's what it gives you in meter. So here you write 0.09 meter divided by 2. It gives you the work done in joule. In joule. That gives you 0.63. 0.63 in joule. That is it. And take a look at that before we do another example. The load of 1,000 Newton is formed. The load of 1,000 Newton is formed on a spring of initial length is decreased to 2.5. Find the force constant. Now carry out this calculation and post your result for me.